Right.
Yeah.
All right. Good evening, everybody, and welcome to the TW's World Constellation at Winslow. Thank you for coming to our. I think this is our second TWed of the fall 2016 season. Although we're interspersing, if you're following the emails, we're interspersing TWed talks with. We've just started up the RPIR users group, which is meeting once a month. It started last week. It's meeting once during October and once during November. Does a little advertisement. You can email me or find me somehow. If you're interested in more TWed talks for this term, it's tw.rp.edu/web/TWed. The schedule for the R users group is also on that. We're doing all sorts of topics, and we think we settled on a name, which is R Pirates, RPI rates. So anyways, so we're really happy to have Matt Klawonn, who is what are you, a third year PhD student?
I think I'm a third year now.
That's awesome. He's going to be talking to us about deep learning, an introduction to deep learning. And are you going to do another talk later in the term?
I can, yeah.
That's awesome. This will be really awesome. We have a couple slides left. We can talk about that. But I'm really excited about this. He promises to talk about a couple different platforms. Please feel free to ask questions during the talk.
Sure.
Okay. All right, take it away, Matt.
Yeah, thanks everybody for coming. I'm Matt Klawonn, as the slide says, and today I'm going to be talking about deep learning. Before we jump right into that, though, I want to give a little taste of some of the applications of deep learning and give some live demos of what it can do. So we're going to be talking about 3 different demonstrations here, an image classification demonstration, some sentiment analysis, and also some visual question answering. And you'll see what those are if you don't know in a couple seconds. So first, image classification. The task of image classification is, given an image, you want your image classification system to be able to sort that image into one or many classes, essentially describing what is the content of the image. So we're going to take a look here at a quick example. A deep learning framework here is doing image classification when I click this link. And here we see this quick example for this famous deep learning framework giving a classification of this image here on the left, correctly identifying that there is a cat in the image, and also giving some confidence scores associated with the predictions over here on the right, and ranking the top 5 predictions in order of decreasing confidence. So you can see a lot of these classes actually end up being related to each other. And deep learning systems are actually to the point now where they are surpassing human level performance on this task. You might ask, well, that's kind of dumb. A human should be able to get 100% of the questions right about whether there's a cat in a picture or not. But actually, some of these data sets get pretty tricky with like identifying between different kinds of cats or different kinds of dogs. And sometimes there are multiple classes within a single image, and you just sort of have to pick which one you think should be the correct class for the given image. So the error rate for humans is about around 5%, and these deep learning systems are now surpassing that. So moving on to the next.
It doesn't say cross-eyed cat.
It does not, yeah. So moving on to our next example, just to show what else deep learning can do. Yeah, question already.
Do you know if they can surpass humans at like CAPTCHAs?
So that's kind of an interesting problem because CAPTCHAs are constantly being evolved so that deep learning or any learning system will have difficulty doing it, right? That's sort of the point, is it's trying to trick the robots and let the humans go through as easily as possible. So I don't know that there's ever going to be a set answer to that, because it's going to be kind of like this cat and mouse game of CAPTCHAs evolving to try to trick these systems. And that's not really my area of expertise, so I can't speak to what the current state of the art is in there. But you know, I would imagine that at any given point, you'll probably have a few CAPTCHAs that are always going to be easier for humans than for these systems. So moving on to another example, more in the realm of natural language processing, there's this task called sentiment analysis, which essentially tries to classify some text as belonging to a particular sentiment. So you want to rate some movie reviews as positive or negative, neutral, that sort of thing. Here we have some example movie reviews about a movie that I'm not sure what the movie is here, but there's a deep learning system that's going to tell us whether these reviews are positive, negative, or neutral. And we can do this live because I can type into the thing. So does anybody have something they want to say about a movie they saw recently, and we can decide whether or not it's positive or negative? Nobody? All right, so we'll go with just the first one here. So this is ostensibly a negative review. We'll see if the deep learning system classifies it correctly.
I think that's a Ben Affleck movie.
Yeah, maybe. No comment. So Stanford is actually being kind of slow today. So maybe if this takes too long, I'll just move on to the next example here. But I've done this example before, and the deep learning system correctly identifies that this is a negative review. And in the really cool state-of-the-art sentiment analysis systems, you can have more sentiments than just positive, negative, or neutral. You can start saying whether or not somebody thinks something is funny or interesting, a whole bunch of different options. And yeah, this is taking too long, so we'll just go ahead and move on. Thanks, Stanford. So another interesting area of research that sort of covers both natural language processing and image processing is visual question answering. The task of visual question answering is given an image and a question about that image, you want to return the correct natural language answer to that question. So here we can select from a variety of images here, and we can ask any question that we want about this image. So does anybody have a question they want to ask?
What is that mountain?
What is the mountain? All right, we'll see what it spits out, but I don't know if it's going to get that question right. What is the mountain? Yes, no, and it's a mountain. Okay, so within the top three answers, it correctly identified that the mountain is indeed a mountain, which is great. And this is not one of the state-of-the-art systems. It doesn't get as many questions right as you'd like it to, but it still gets some of them right. And these things are constantly improving. And the thing that all of these different applications have in common is that they rely on deep learning. So with these examples in mind, we're going to talk about these different aspects of deep learning. Firstly, what it is, why we want to use deep learning.
Actually.
Yeah, sure.
So actually, I challenged it. So what if you asked instead, what is the name of the mountain?
What is the name of the mountain? Yeah, it's probably not going to get it.
Is it just based solely on image content? It doesn't look at any other like metadata, like if the image is geotagged or whatever?
This specific model uses only...
Well, say just ask like, where is this?
It's probably not going to get any of these right because I'm sure the name of whatever this mountain is, I don't know, is probably not in the vocabulary of this system.
Sure.
So we can see what it spits out for this. A pine winter ski. Yeah, see, these are all pretty generic nouns. I don't think it has any proper nouns in its vocabulary.
But like if we ask like how many people are in the image?
Oh,
yeah,
right.
it would probably get that right.
I guess we're all just two.
I got it wrong. It says 1, 5, or 4, but it's maybe seeing shadows or something like that here. Yeah, so I didn't make this, but it's just kind of shows you different applications that it can be applied to. So with that in mind, yeah, maybe there are. Maybe we just don't know. With that in mind, we're going to talk about what deep learning is, why people are using deep learning at an increasing rate, how people are using deep learning, where you can start if you're interested, and also we'll go through a coding demo to show you how to implement a simple deep learning model in a popular framework. So first, starting off with what deep learning is, it's important to recall what machine learning is in general, because deep learning is a subfield of machine learning. So the problem of machine learning is given some unknown target function, some training data and a hypothesis set. We want to use a learning algorithm to produce a final hypothesis which approximates the unknown function that we're interested in. So say the unknown function is some credit approval formula, something that lets you decide whether or not to approve somebody for a loan. And you have some information about that person, like their age, their income, their gender, that sort of thing, and also some historical records of banks in a bank of loans that you've previously handed out and whether or not a person defaulted on those loans. Then your machine learning algorithm would essentially attempt to approximate that function that tells you whether or not to give the person a loan in the first place. So with that in mind, we'll look at the difference between traditional machine learning and deep learning. In traditional machine learning, we have this problem of trying to approximate a function, and we're given some information about our training data, which are called features. So this is best illustrated just by giving an example here. We have features of different kinds of apples. And you can say an apple has a color, it has a type, it has a shape, all of which tell you something about the apple and might tell you something about your function which you're trying to approximate. So you could imagine somebody's personal preference for apples might be based on how it tastes or the color or the shape of the apple. And in the traditional machine learning approach, all of these features are sort of handcrafted, right? A clever human sits down and thinks, what are the important things about apples that I need to model for this problem? And they generate training data that has these annotations. So you would feed not images of apples to your system, but rather the collection of these attributes which describe the apples in your training data. So that important part to remember is that these are handcrafted. Whereas in deep learning, you'll see these are features on the right here. This particular deep learning model looks like it's going to be applied to some sort of like facial recognition or something like that. And you can see that the features on the right here might represent different aspects of what a person's face is like. A person's face has eyes, a mouth, nose, jawline, that sort of thing. And the big difference between deep learning models and traditional machine learning approach is that these features, i.e. a person has an eye, a nose, etc., are learned by the model itself. So a person does not have to sit down and decide what constitutes a face. Rather, it just passes images of a face and lets the deep learning model decide what the important features are. So that's the biggest difference. And typically when we refer to deep learning models, we're talking about neural networks. So neural networks are biologically inspired. They come from the idea for them essentially came from seeing how people's brain worked, although they're not exactly the same as a brain. In fact, they're pretty different. But they're machine learning models which rely on neurons to compute that function that we're interested in approximating. And they learn to approximate that function by intelligently updating the weights of the connections between neurons. So this is sort of similar to how it works in biology. You have different neuron connection strengths in your brain, and when one neuron fires, if it's like strongly or weakly connected to another neuron, it influences your decision-making process in varying ways depending on that strength. And that's how people learn too, is by adjusting the strengths of the connections in between the neurons along with other things. So going back to that previous example of the deep learning model we saw, you can see that the neurons are organized here into these different layers. And then these lines in between them are the weights which get adjusted during training to try to approximate the function. So this is done real quickly, not to gloss over this because this is kind of an important point. But this is done via a back propagation algorithm, which essentially computes the error between what you predicted for a given set of inputs and what the correct output should be. So if you're, again, going back to a credit approval scenario, if you predicted that you should give a person a loan when you should not have given that person a loan, then that error needs to be propagated back through the network and the weights need to be adjusted such that your model has a better chance of getting that question right the next time, right? And so the back propagation algorithm was invented to do this. Basically, it computes the error for a given layer and then adjusts the weights according to the gradient of that loss function. So you're taking a step in the right direction to try to get a lower error the next time around. And then the clever part of backpropagation is that we can do this going back layer by layer through the network because of the chain rule, actually. So the chain rule allows us to compute a gradient for each layer going back into the network based on the error of the layer ahead of it. And we can see an example of what a neural network looks like when it's learning. This is a YouTube video. So you'll see here that the inputs are data that's being passed into the network down in the left, and we have a desired output for each input, which is up in the top left there. This is a really simple function, and there's only 7 training examples given. I think this is, I didn't pay attention to what this is, but it might be like an XOR function or something like that. And we can see that for each input, the network fires a little bit differently. And as it learns, we see the strength of the connection between the neurons being indicated by the width of the band, the width of the connection between them. So right now, this network, or that weight is growing really strong. So the network is deciding that whatever the output of this neuron is pretty important for determining how to classify correctly the input that you're giving here. And the difference between red and green is just positive versus negative weights. And as it learns, you see the average error is going down up in the top right there. And eventually, it'll converge to a pretty good error rate. So once it gets down to about 1% or less, you know that you've approximated the function pretty well. And this didn't take too long or too many training examples because this was a pretty simple function to learn, whatever it may be. Yeah, so you can go ahead and stop that. This video had music for some reason. I don't know why, but I muted my computer, so. So now we know a little bit about what deep learning is, right? It's a machine learning model that learns features, what features are important in order to perform the task that you're interested in. So now we are going to examine why we want to use deep learning as opposed to potentially other machine learning methods. So just to give a little bit of background on the history of artificial neural networks, they sort of came along in the form of what's called multi-layer perceptron. Perceptron is essentially just a linear classifier. So if you remember back, I'm sure everybody's done some sort of like linear regression to fit data at some point. Multi-layer perceptron is essentially a bunch of those linear classifiers stacked on top of each other, with the key addition that some nonlinear transformation function is applied to the line which is determined by each perceptron. So the backpropagation algorithm that I talked about a little bit, well, it came around in 1985, and it proved an effective way to train these things. And then these things came along called convolutional neural networks, which I'll get into a little bit later. Essentially, these are neural networks or deep learning neural networks which are particularly useful for vision problems. They attempt to mimic primates' visual cortex in their construction. And then a famous example of a convolutional neural network came along in 1998, which was used to classify handwritten digits. So it could basically recognize what people had written down for postal codes on envelopes and that kind of thing. And it was sort of the first example of a neural network that had real effective application in practice. And then in 2006, this is where we start to see the explosion of the use of neural networks and deep learning models in practice, because they came up with some techniques that made them really effective and really popular. And we'll get into all of that later too. So it didn't work really that well at first. You saw 1961, 1986, and it really took until 1998 to get even just one good application of neural networks, and then until 2006 before these things started being really applied in practice.
Actually, can I ask a question?
Go for it.
Before there was backpropagation, how did they actually learn?
So it was just, there was a proof done that these multi-layer perceptrons with just linear activation functions were equivalent to a single linear classifier. So you would train it essentially how you would train any linear classifier. Just take your features, project them into that feature space, and then do like some kind of linear regression or perceptron learning algorithms to learn. But then this back propagation came in, which really allowed for the expansion of neural networks beyond just these simple feed-forward linear activation function type things, and allowed for more complex structures. Yeah. So addressing some of the reasons why neural networks weren't so popular for a while, they're crazy expressive. They can approximate any continuous decision boundary. So I don't know if that made sense to anybody, but basically if you have any function that you want to approximate, as long as it's continuous, and I think smoothness might also be a requirement, then a neural network can in theory learn it, which is super powerful. That's a massive class of functions that you can learn with these models. But the flip side of that is that they can end up overfitting your training data. And essentially what overfitting means is you're giving too much weight to individual points, and you're not looking at larger trends of the data. So this is a real problem if you don't have lots of training data to give you a really good example of what a really good view into what your target function looks like. So here we see two graphs. The one on the left is not overfitting, while the one on the right is overfitting. You can see it's varying wildly with each of the points. And neural networks are really notorious for being bad overfitting models, and they still can be sometimes. And there are also some theoretical training difficulties when you're dealing with deep neural networks, especially. The more layers you have, the more this becomes a problem. So we saw an example of backpropagation earlier. Essentially, what backpropagation relies on is the ability to propagate an error back through the network so that each layer of your neural network is continuing to learn. The weights get adjusted so that you're approximating your target function a little bit better. But the problem is when you have lots of neural network layers in your model, sometimes you can have what's called a vanishing gradient problem, where that error that gets propagated back through the network essentially goes to zero, and the layers that are earlier on in your network then stop learning things. Or you can have the opposite problem where your gradient in fact explodes as you go back. So it starts getting bigger and bigger, and then you have a similar problem where you're not learning anything useful in those previous layers. The weights are getting updated way too fast. The adjustments that you're making are way too big. Yeah.
Why does the arrow go when it goes back? It comes to zero.
So if you have, it's all about how you calculate the gradient at each level. So the error at this level will be based on, and the weight updates that you're going to make at this level will be based on the error at this level. And so if your gradient that you're computing here is small, maybe you get a smaller gradient computation here, and then a smaller one here, and then so on and so forth as you go back. And if that drives towards zero, and eventually you're not updating your weights that are early on in your network at all.
So regarding to the previous slide, when you say overfitting,
yeah,
is there any way to overcome this overfitting problem, like
regularization?
Yeah. Well, I mean, it seems like at that time there's not a lot of training data, so I mean, overfitting is
right. So training data was a little sparser back in the mid '80s than it is today, and that was one of the problems. And I'll get into all of the reasons why they're better in a little bit if you'll bear with me for just a second. So this is one of the reasons, and then another reason. Everybody remembers the CRT monitors from back in the day. So there are some practical training difficulties beyond just the theoretical ones which you have to overcome. Essentially, older machines were not sufficient to realistically train these deep networks. The deepest network that you'll see from back in the day is maybe like 5 layers deep. These things require lots of matrix computations to train, and CPUs, GPUs, memory, all of these things were just sort of insufficient to train these models, which have lots and lots of parameters that you need to be updating. So getting into what changed, we have improved regularization methods. We have some tricks that we can use to overcome these exploding and vanishing gradient problems. We now have lots more data available. So that was one of the big reasons, is these models are really data hungry, and now we're generating images and textual data on the order of petabytes daily, more than that, probably terabytes which are all accessible via the web. So there's really, for most tasks that you're interested in these days, I don't know if I want to say that. For a lot of tasks that you're interested in these days, you can find training data readily available. And we also got some beefier machines, right? So the gaming industry actually played a huge part in getting GPU technology to the point where now these matrix computations, which deep learning models rely on so heavily, have been optimized on these graphics processing unit platforms because it's the same operations that you need to render video game graphics. So all of these are reasons why deep learning is more popular these days.
You're saying gaming is saving the world?
Yeah, well, it's pushing AI. It definitely is, because not only are you getting beefier hardware, but then also, game AI techniques are helping advance the state of the art in that regard. So the question sort of still remains: why do I want to use a deep architecture as opposed to the old days when we had these? You just thought a little bit about the problem, came up with some features, and then ran it through whatever machine learning model you had. And the simple answer is they're way more efficient representations. So that claim that I made earlier about neural networks being able to approximate any continuous smooth decision boundary, that applies to a network that's I think only 3 layers deep. But the trick of using these deeper architectures, ones that have lots of those layers, lots more neurons stacked, like we saw earlier in the picture, is that they are more efficient representations, meaning you need less overall neurons if they're stacked on top of each other like that to approximate the function than you would if you were using a shallower architecture. And we can see an example here. This is from the paper which essentially proved this. We see a decision surface here, the wavy line that we're trying to approximate. And if you're using a Gaussian process like they do in this, they show that you need at least 10 of these Gaussian processes to approximate this decision boundary correctly. Whereas, this is much more easily approximated by some kind of deep neural network architecture or deep learning model.
So there's a beautiful example of this. Yeah, you can find it on YouTube, where this graduate student gave this talk last year on implementing deep learning, convolutional neural networks on Babbage's analytic engine.
Oh yeah, I think I saw you sent out the link to that.
Yeah,
right?
Yeah. And why that worked was, and why that talk is beautiful, is because it's all in the efficiency argument, the efficiency that comes from the layers.
Right. Yep. Yeah, it's the same kind of thing.
So efficiency, you mean efficiency in terms of training the model, or efficiency of running the algorithm?
Efficiency in terms of the number of parameters that are required by the model. So if you have if you're trying to approximate a complex function with a neural network that's only like 2 or 3 layers deep, then you're going to need lots of neurons in each of the layers to approximate it well. And chances are you probably don't have enough training data to adjust all of those weights the way that it should, even though it's theoretically possible. So these deep learning architectures are, for certain classes of functions that you're trying to approximate, you're more likely to have a chance with a deep architecture than you are with a shallow architecture, because it doesn't have to search through so many different combinations of parameters.
So in a deep architecture, in each level, each layer, there will be fewer neurons compared to the shallower one where multiple neurons.
If the function is sufficiently complex, yes, that's essentially what this paper is showing. Yeah. Okay, so deep learning and you. Why are you all here? You're thinking about using deep learning, or you just wanted to, or I made you come. Everybody here in here falls into one of those two classes.
My algorithm found the pizza.
Yeah. So if you have lots of data, if you have sufficient computing power, and if you don't really have some key insight into your problem, you don't really know what features are relevant to the problem that you're trying to solve. And this is usually the case with like complex vision problems, like detecting somebody's face. We can all recognize, unless you have that disease, prosopagnosia or whatever, I butchered the name, but you can all recognize somebody's face, but it's hard to describe what makes that person them, right? So the deep learning models are really good for these problems where you can't necessarily come up with the right features that are necessary to solving your problem. So use deep learning if you have, at least these three factors. If you have some really good idea about how to solve your problem, what features to come up with, you should always go with that approach because of the principle of Occam's razor. Simpler models are always better when you can get away with it. But nobody in the world has come up with the key insight into solving, facial recognition problems or anything like that. And in fact, the handcrafted features, which they used to use for these kinds of problems, have been blown out of the water by the features which are learned by deep learning models. Yeah.
Can you use the features that a deep network will construct to pre-process for like a simpler method?
You absolutely can, yes. So that's one of the really cool things is that, and this is commonly done in practice, we saw that deep architecture before where all of it was a neural network and each layer would correspond to learning some different feature. So eyes, noses, et cetera, et cetera. And one of the really cool things that you can do is instead of having another neural network layer at the very end of your deep learning model, this is why it's called deep learning and not just deep neural networks, is because you could apply some other like classification algorithm on top of it, like an SVM or decision tree, things like that, and take as input to that SVM or decision tree the features which have been learned by the deep learning model. And in fact, some of those kinds of approaches are really effective in practice, taking these deep learned features and then applying them in other more traditional machine learning techniques.
Is it frequently the case that you can look at these features that are constructed and see that they have like an intuitive meaning, like, oh, this is a face?
Yeah, so this is actually an emerging area of research. The people at first were just kind of concerned with making these things work, and now people are starting to wonder a little bit more what these networks are actually learning. So one of the common techniques to figure out to visualize what your intermediate layers have kind of learned, what your neurons and groups of neurons correspond to, what features they might correspond to, is to feed in images of what you, or you can actually calculate what input data would maximize the spike maximize the activation for a given neuron, and then that will tell you sort of what feature that particular group of neurons are. And the visualizations that people have generated are actually pretty trippy and kind of cool to look at.
Are those swirly things?
Yeah. So you'll see like a really swirly thing that like kind of looks like a nose, but so you would say, oh, that neural network learns a feature which like kind of looks like a nose. And in fact, I don't know if people are familiar with Deep Dream, but it was sort of a visualization neural network that Google came out with in July of 2015, I think. And basically what they did was they fed the activations of the neural network layers back into the network. And so that signal that each, like the groups of neurons were generating was like strengthened via this feedback loop process. And what ended up happening was the images that they would feed in started to like grow these features that had been learned by the network. So these networks are typically trained on data that has lots of cats and dogs. So randomly, like people's faces would morph into a cat's face, and they would project like different kinds of buildings into landscapes where there hadn't been buildings before. It's really cool. Yeah, that visualization stuff is really interesting research. Yeah, so it's not all fun and games with deep learning, though. There's lots of legitimate complaints that have come from both people outside machine learning and people within machine learning about these models. One of the biggest ones is that there's very little in the way of deep learning theory. So these things ostensibly work in practice, although we'll get into that in a second. But we're not really sure why they work. And oftentimes, people, in order to generate these models, don't go by any like mathematically principled in a strict sense of the term, methods. Rather, they rely on a set of tricks, which has sort of just been developed over the years as people have tried more and more things. And one of the most common responses to asking somebody why they did something the way they did is because they'll say because that's the way that it worked. So this is an example of a neural network which Microsoft proposed, I think last year or maybe even this year or something like that. That's called a residual network, and basically the difference between this and the simpler versions that we looked at earlier is that output from some layer is then fed directly into a layer that's 2 layers ahead of it in the architecture. And actually the talk that was given by the Microsoft researcher when he presented this, because it achieved state-of-the-art accuracy on some data set and was kind of a big deal. But somebody asked, well, why did you feed it forward 2 layers ahead? And his response was because 1 and 3 didn't work. So you'll get even crazier versions of that same anecdote than that, depending on which sort of paper you're looking at. There was another one. One of my colleagues had gone to a computer vision conference and asked why the person had used this specific architecture for the computer vision problem they were trying to solve. And they said, well, actually, we tried this on speech data first. They were trying to convert human audio speech into text, but that failed miserably. So we tried it on image data, the same architecture and same kind of training methods, and it works better. It worked up there with the state of the art. So this is a legitimate complaint that people are just kind of trying things and throwing spaghetti against a wall and seeing what sticks, which is makes it a little frustrating to be a researcher in the area. And there's also
and they're being judged by competitions as well.
Yeah.
So things work and they win competitions.
Right. And well, that's the thing. Another problem with this sort of insane competitiveness and fighting for those extra little bits of percentage points is that nobody uses a concept of statistical significance. You can report a result that's 0.4 percentage points better than a previous state-of-the-art model for a given data set or something like that. Get a paper published, no problem, but nobody stops to ask, is that model actually any better, or did you just get a little bit lucky with how your network trained? So yeah, these are complaints that people that are way smarter and have more clout than I do are making also.
Yeah, sounds a bit like, get off my lawn.
Yeah. Well, the Michael I. Jordan is the name of a famous machine learning researcher, and he's actually the Michael Jordan of machine learning research, and he has voiced some of these complaints also. And then there's also a question of whether or not this stuff is actually working, or if we're just beating a bunch of data sets to death. And it seems like it's working on those data sets, but then in practice it would fail miserably. So these are 2 images which are imperceptibly different. You cannot tell that this image of a panda on the left and the panda on the right are different, but there is a small amount of little noise that's been added to all of the pixels of this image. And on the left, a deep learning model classifies that as a panda with 60% confidence, and the right one is actually a gibbon with 99% confidence. So there's this question about how well these things are actually learning, and that when you tie this kind of problem in, this is called an adversarial learning problem or something like that, where you're trying to trick your model essentially, and clearly it doesn't take too much to trick deep learning. And actually, this is a problem with a lot of machine learning models. But the real danger of deep learning models when you couple it with this adversarial problem is that we don't understand how these neural networks work. They're essentially black boxes. So if you were to deploy this in a real world and it failed miserably on whatever task you had thought you trained it for, but it went out of the real world and sucked. With some other machine learning model, you might be able to go in and pick at the details of it and say why it failed. With deep learning models, that's almost impossible. And it's potentially a real problem. So it's things to be wary of.
So there are 2 things that come to mind. The first is steganography, image watermarking. Looks like noise. I mean, that's essentially how it's implemented. It's evolved over years in terms of complexity. So so a question I have in mind is if you've got an image and then you've got an image with a watermark, when they go through these deep learning processes, how does that
don't
imperceptible
know.
change actually affect? And that's just a question. The other thing is in terms of the explanation of these things. That's one of the questions I actually have for you is how is that developing now in terms of?
Yeah. So going back to that that visualization research that I talked about earlier, seeing what groups of neurons tend to activate on which features of your data. That's sort of the biggest push towards understanding what's going on the inside of these, is examining when certain groups of neurons or certain structures are firing for given inputs. As far as like trying to come up with some theory, there have been some attempts at explaining these things a little better. One of which is, I don't know if people are familiar with Gaussian processes, but there are actually people that are theorizing that maybe these deep learning models are not that different from what's called a deep Gaussian process, which is a little bit easier to understand. But yeah, so this is, I'll get into this a little bit later too, but training these deep networks is, it's a non-convex optimization problem, which is NP hard. So until somebody solves P equals NP, there's not like a guarantee that we're ever going to completely understand how that non-convex optimization is going to behave. The best guess that people sort of have right now is, I don't know. Yeah. So yeah, another reason to potentially be frustrated, but it's not all bad. It's not all good. It's not all bad. And I touched on some of those tricks earlier. People are sort of relying on tricks to get these things to work for different problems. So we'll jump into that a little bit now, understanding what to do. So getting back to your original question about how we can regularize these things such that they're not constantly overfitting the data. Obviously, more data helps. These things are very data hungry, but you can also use regularization techniques that are common practice in other machine learning methods, like early stopping. So you set some of your data aside during training time and you don't train on it, but you check against it every n training iterations and see if your error or your accuracy on that data is still going down, which is what you want. You want to get lower error, or if it starts increasing again. And basically what early stopping is you say, once I start seeing that out of sample data I'm starting to do worse on, I'm just gonna stop and call it there. And this graph illustrates why you would want to do that, because that training data that you're using, you might start to overfit it. You might start to get really good accuracy on that, but then worse accuracy on the data out of sample, which is what you care about anyways, right? Because that out of sample data is what you're going to end up classifying in the end. That's the whole point, is that you don't know the labels for this stuff, and I want to get really good accuracy on those data points. And as I touched on before too, these are optimizing a neural network is a non-convex optimization problem. And what I mean by non-convex, for those of you who aren't familiar, non-convex function is something which is, it varies. It's not entirely convex throughout the function. So you have all of these local minimum, which are different values potentially than a global minimum, which you're trying to reach. So how optimization techniques usually work is some kind of hill descent or hill climbing algorithm, where you're trying to follow this function down to its lowest point. And when you have just a smooth single hill essentially to climb down in a convex function, that's actually pretty well understood. We know how to go down the hill, but here you might start at a different point on the hill, and you might end up in a different local minimum depending on where your initializations were. So that's why for these problems, it's really actually pretty important where you start, and also really kind of frustrating because you might start somewhere and your model might be pretty good actually. And let's say this was the local minimum and that was the only other minimum here. If you started in the wrong spot, you could still see that you're getting like really high error when in fact your model is pretty good. And your loss function isn't too complex.
How do you know what the correct place to start?
Yeah, so there are So there are ways to initialize your network so that at least you're learning something and you get to a pretty decent local minimum, even if it's not a global optimum. And those initialization strategies involve means of making sure that you're avoiding vanishing or exploding gradient problem, and also your choice of hyperparameters for your the optimizer that you're using, basically the algorithm that you're using to descend the hill. You can adjust things like learning rate, and there are other various analogies to this physical analogy called like momentum. So if you're like really going down a hill and it's really steep and you're really improving your error rate, you want to keep going as fast as you can in that direction because obviously you're doing something right. And sometimes if you adjust those parameters just right, you can end up using them to escape local minima like this, and you might climb right out of that using this analogy of momentum or what have you, and get down to some better optimum. And actually, those are some of the most important things to cross-validate for. So if you're going to adjust any one thing when you're training a neural network, it would probably be like your learning rate. So try it with a few different kinds and then see which one of those gives you the best error on your validation set. Right. So yeah, that's actually kind of the subject of a paper that I just wrote. Is that it's hard to do that kind of cross-validation for these models because they can take weeks to train based on if you have like hundreds of thousands of images that you're training on, that sort of thing. So having a good guess is important, and there are people that have essentially kind of settled on, hey, this is probably the range that you want to look on for most functions that people are using these neural networks for, like image classification and that sort of. And so the paper that I just submitted, well, I won't say because technically it's an anonymous review, and I don't know who's watching. So, so other tricks, as I said, these models are really data hungry. So this is another sort of regularization technique, but not really. You just want to prevent it from overfitting by giving it more examples to work with. And so you want to do some kind of augmentation to your data set. Create new data points that you can then use to further help train the model. And you can do this using like really stupid, simple techniques, like if you're writing something to identify license plate numbers, just superimpose different backgrounds on the same license plate number a few times. And if you do that for all of the license plates that you have in your database, you can triple or quadruple the size of your data set to help you stop overfitting. You can also do things like rotating images or adding a little bit of noise like we saw in that previous example and saying that they're the same thing. And you can end up generating lots more data for your model to train on this way. And then there are a few neural network specific regularization techniques, specifically one that I'm thinking of. It's called dropout. Dropout essentially involves training.
Actually, before you get on this, can I ask a question about that previous thing?
Yeah.
I realize it's sort of dangerous to anthropomorphize this, but when you're talking about that, when you're talking about taking that sort of known and putting it in different contexts, in different ways, and flipping it around and that sort of thing, it seems like it's equivalent to how we learn. So we can identify face when the face is in any sort of orientation.
So that's so it was. Rotating is not necessarily a good example for vision because the mechanisms, so convolutional neural networks based on mammals visual cortex. I said primates earlier. I think it's just mammals. They all share like a very similar thing. Are the operations that are performed are actually scale and rotation invariant. Rotation invariant, at least. Maybe I shouldn't say scale. But yeah, so it's we'll look at an example. I actually have a nice animation of how a convolutional network works. But basically, rotating an image might not be the best way to get something new because that operation that's being performed doesn't really necessarily care that it's one way or another.
I see. So in terms of extrapolating to something like audio, there's similar things where we have this ability to recognize musical patterns.
Yeah.
Despite how torture them.
Yeah, so that sort of stuff might. So I had a good response for visual stuff. The other stuff I'm not as sure about, but I would guess that a lot of that is just our brains are pretty well initialized to the sort of things that humans are supposed to be good at via hundreds of thousands or millions of years of trial and error. We have that advantage. So it might just be that we've got a really good starting point too from how we're how we develop in the womb, and yeah,
You're saying we might be somehow optimized.
Yeah, I don't know about optimized because genetic
well, that's
algorithms are always
yeah.
a little funny, but
Right.
yeah, we've gotten to a good point where we're pretty good at doing human things. So jumping into more regularization techniques, this one is actually over the past like 2 or 3 years has been one of the biggest keys in getting deeper and deeper networks and better performance. So the idea of dropout is essentially with some probability that you determine for each layer, you just ignore that layer's activation function for a given training input. And then at test time, you treat your network as its fully connected variant, and you just scale the output of each activation function at each neuron by the probability by which it was dropped out. And what that equates to is essentially doing an ensemble method of lots of these skinnier networks. So you get essentially votes from all of the exponentially many ways that you can permute the dropout of the network and get a vote between them in the end by doing this scaling trick. And it's a pretty cool trick because it's like super efficient at test time because you only have to perform that one operation. And that's one of the many regularization methods that you can use with this. You can also do things like stopping weights from being too big or too small, so restrict the norm of the weights to be within a certain range, which is common to multiple machine learning techniques. And then sort of lastly, another trick that people do is they'll just reuse models and potentially just add like a couple layers here or do some kind of small tweak to them. But like we were talking about before, where you can just stick it, you could take the features learned by a network for some task and stick them on top. If say I'm doing some kind of image recognition and I see that a lot of the images in my data set are kind of similar to images from a data set that another model has been, a different data set that another model has been trained on, I can theorize, hey, maybe those features that were learned by that model are useful for this task that I'm about to do. And I just take those weights and that model that's been trained before, and I add a layer, something like that, or leave it alone entirely and just train a new classifier on top of those features that I can generate for my model. And this is shown to be pretty effective in practice. Even if you don't just reuse their weights, the reusing like architectures in general is pretty common. So there are people who have applied the first like really deep neural convolutional network model called AlexNet, and there are people who have applied it to all sorts of crazy stuff, like use it for determining like 5G bandwidth at a particular area and stuff like that. Stuff that isn't even visual data, and it does surprisingly well on it. You think, well, that's kind of crazy. Why would something meant for vision do well on this? That's not how humans work, but there's always the argument that, well, maybe you just can't feed your visual cortex radio frequency data. Maybe you'd be really great at it. Yeah.
So like when you're designing your networks architecture, is there any expectation that you're going to draw upon domain knowledge or anything, or you just like throw a random shape and see?
Yeah. So getting back to the sort of the dark side of deep learning, no, aside from saying that these convolutional networks are pretty good at image data because they quote unquote are replicating mammalian visual cortices, or there's another kind of network called like a recurrent network with various kinds of layers that work well on natural language data, and there's some like intuition that, hey, this is kind of like how the visual cortex of humans works, maybe it'll be good for vision, or hey, this looks like it might be how we remember text that we've seen. Maybe it'll work on natural language data. aside from those sort of like very vague hand-wavy intuitions, there's not really a lot in the way of saying this is the right architecture for this specific problem. A lot of people's solution is to just throw more layers at it. So yeah, it's a little unsatisfying, but if you're not a machine learning researcher and you're just interested in getting something to work, it can be okay. Okay, so just briefly touching on where people can start if they're interested. There's lots of deep learning frameworks out there. So the first one that came along was Theano. That was done by a group up in the University of Montreal, I think. And then a couple have been built on top of Theano. So Theano is more really of an abstract manipulation, like a symbolic manipulation library. And then more like neural network grounded frameworks include Keras and Lasagna. And then Google recently released one, actually, was that 2015 or 2016?
No, it was 2015.
2015, yeah. So they released TensorFlow, which is sort of their deep learning thing. They built that program that beat a Go champion using TensorFlow, I believe. I would hope they use TensorFlow, seeing as it's their baby. And then Caffe is a common one for image processing, image-related deep network architectures, and also Torch. So Caffe is University of Berkeley and University of California, Berkeley, and then Torch is Facebook's baby. And then there are tutorials for all of these. These are all links, by the way. If we can post the slides somewhere. You can click on these and see where they go. I just wanted to let people know that there are resources out there. And then if you're just interested in fiddling around with some data, you don't have like a specific task in mind, there's lots of different data sources for lots of different tasks. So looking at MNIST, handwritten digits, ImageNet, classification, picking out cats from the dogs, that kind of thing. Visual question answering, we saw an example of that before. Machine translation data sets, so going from like French to English is pretty common. And then also these like sentiment analysis data sets. So yeah, that was most of my talk, and we can jump into a coding demo if people are interested. I've got some example code in a particular framework. I don't know what the time is. I can't see.
Well, we're actually 3 minutes to 8.
Cool. Okay, so I timed that about perfectly. So we can go run through a quick tutorial showing like what code looks like for classifying different data. So if people are really, I've been talking up these convolutional neural networks a bunch. I can finally kind of explain what they are. So they are basically applying this a scan called a filter or a feature map at different parts of an image, and each feature map is looking for a different feature in the image to activate its neurons essentially, and they exploit this. The spatial layout nature of images to achieve this. So we can look at an example here. This has been running the entire time. You just haven't seen it yet. So we have these filters here, which correspond to the features that we're looking for, and they're applied across different channels of the images. So this is like a red, green, blue image where you have the 3 RGB channels. And the filters are applied in a sliding window manner across these images. And this is how, apparently this is how mammalian visual cortices work, is by sort of looking for these different features, scanning the visual data that you're processing, and picking out the relevant features that you're particularly interested in. And then those filters are basically multiplied by the channel values of the original image, and then summed up, and they produce these output volumes. And then, again, the cool thing about using deep learning to do this is that the values in those filters are going to be learned to be optimized for whatever the task is at hand. So those are pretty simplistic, 1, -1, -1, etc. But in reality, you'd probably see a wide range of continuous values, and each filter would correspond to looking for some kind of feature.
This is implemented in.
This is JavaScript.
Okay. No, I know that this is JavaScript doing this stuff, but I meant in terms of what is it actually illustrating? Is it illustrating R code, or is it
JavaScript? It's all JavaScript.
Oh, it is JavaScript.
It is.
Okay.
Yeah. It's not, yeah, it's not just being rendered by JavaScript. The variables here are also JavaScript. So nothing's actually being computed here. It's just essentially in like different numbers laid out across the screen. So here's some what some example code would look like. You read in your training data and your test data from your data set that you're interested in, and then you would do your pre-processing. So here we're going to normalize all the values to between 0 and 1 for your image data, and you can perform all sorts of other things like adding noise and that kind of stuff. And then you essentially just create your model. So this is using that Keras framework that I talked about earlier. You create your model object, your sequential object, and then you start adding layers like we see here. So we have this model.add command, which is going to tack on a convolutional layer to start the network. And then you keep adding layers until your the network architecture that you want is there. You compile your model, you specify what your target function is, what your loss function is, and you specify which optimizer you want to use and anything that you want to keep track of during the optimization process, like accuracy, for example. And then you just say, I want to fit the data. So you call the model.fit on the data that you have, and it will train for a long time or a little time, depending on the size of your data set. And then to test, you just say, OK, now evaluate this on the test data that I have. And that will give you some kind of indication of how your model did. So there's a lot of further reading and references in there that I can, if we post the slide somewhere, people can look at. And with that, I'll take any questions.
So let's questions for that?
Did you have a question? Yeah, sure.
Oh yeah. So, so my question is, from like 3 or 4 years ago when I took the main course, the instructors that the beauty of machine learning is that you don't have to basically specify any single parameter of your target function in order to provide a best model. What you do is you basically fit your target function or something like that. Your function into a hypothesis, except where multiple hypotheses can be a very valid kind of one solution model of the training data. So when it comes to the problem of understanding how each neuron works in each level, each layer, you said that people currently do not know exactly how deep learning is working. So I'm wondering if that is an training research topic right now for deep learning researchers, that they are trying really hard to understand how each neuron actually works in order to improve the efficiency or some performance. But on the other hand, machine learning does not require the users to spend any effort on specifying any parameters, which kind of contradicts. Okay.
Say the last part again.
So what I mean is that like suppose you have a machine learning model like TWed, right? And what you do, there could be a solution model there, target function there, and the model is trained from training data.
Mm-hmm.
And the actual parameter is learning is actually generated by learning the data instead of like you specify what actual value is, right?
This is the same way. So this I'm just specifying training data, and I'm letting it learn based on
initial values to each parameter and just let
you have to initialize an SVM too. It's just not as important.
Right. Okay. So my question is it possible that suppose each researcher understands the mechanism of how a neuron works? Is it possible that use this mechanism to improve the performance of neuron people?
So we generally understand how each neuron works. The real challenge is understanding how everything works together, right? So a single neuron without any kind of like fancy activation function on top of it or anything, it's just a linear classifier. The real power of these models comes when you start cascading these linear classifiers on top of each other. And at that point, you start approximating non-convex functions, which is where that complexity gets introduced. And non-convex optimization is not a well-understood area of optimization theory or machine learning research. So that's really where that we don't know comes in. Is it's not that we don't understand how a single neuron works. In fact, we can analyze how it works for a given input data, but rather it's, how do this massive collection of neurons with, millions and potentially billions of weights between them, how do they all interact together? Once you get a model of that size, it's a black box. You don't know. Once you send a signal in, you don't know. It's really hard to understand how it's going to get bounced around and how it's going to go through and understand what's going on at each computation that model is performing. I hope that answered the question a little bit.
Right, but it is possible that people can know what's going on.
Is it I don't know that we know it's possible. I don't know that we know we're not fighting a losing battle to begin with. I'm not sure if any theories come out that say, hey, this is I don't know. I don't know that you can say that generally about this class, essentially this hypothesis set, right, which is a neural network with so many parameters, et cetera. And the other thing that's kind of difficult is when I say the word deep neural network, that could mean a variety of things because you can have different combinations of layer types, activation functions, different sizes of layers, different regularization techniques. So to say anything general about that class of really powerful models is tough. Any other questions?
So for maybe simpler non-convex optimization problems, sometimes it's possible to partition your search space and then more efficiently explore it and maybe get a better guarantee that you're within some percent of the global optimizer.
Sure.
Is that possible with a deep network, or are you just
there are
parameters?
There are theoretical bounds, as there are with any machine learning model, but they're ugly. So if you want a good theoretical bound on how well your model is going to do, you could analyze what the VC dimension is, if you're familiar with that, for your given model, given the number of weights that you have, given the number of free parameters in the model. But and then you would need, in theory, you'd need some factor times that VC dimension for the neural network that you have. But when you're talking about millions of parameters and then you're multiplying, the VC dimension is extraordinarily high for a model that complex. And then you're multiplying that by some constant factor. You need more data than exists in the history of humanity in order to guarantee some kind of good result.
But do you know if it's possible to say, okay, I have so what I have is a local minimizer for my training data, and because of some bound, this local minimizer is within X% of the global minimizer for that particular training data. So not with
right. That's sort of what I was getting at, is that you can get a theoretical bound on it, but it's reliant on also having enough training data for it. So it's not as simple as a k-nearest neighbors where you can say whatever local minimum k-nearest neighbors classification comes to is too optimal of the thing. There's no easy formula like that to come up with that same bound for a deep network that I know of. Seems like a big thing to miss, but I might have missed it.
So I can't really miss the first part of this question. So
what is a neuron?
What part did you come in at?
What is deep learning?
No, it's not. So I know that. So you mentioned that deep learning is capable of dealing with big data set, and when it comes to small data set, deep learning probably won't work well. But other than that scenario, what other scenarios that deep learning cannot do?
Cannot do?
Yep.
So it basically anything where you don't have enough data to train it. So you need enough data that you're not just going to memorize your answers. I don't think I've ever seen any network that's any kind of complex trained on less than 5,000, 10,000 training examples. So yeah, things like domain areas of machine learning like active learning or online learning are really deep networks have not made it into that space just because the size of these networks it's prohibitive. You can't get any kind of good results with a model with that many parameters in those kinds of data constrained spaces. And as far as like other paradigms of like unsupervised learning, there might be some work, but typically when people are talking about using deep networks for a machine learning problem, they're talking about supervised learning, right? With supervised learning in areas where you have lots of data available.
So why don't we let Matt finish his dinner and say thank you?